So the aim of the fourth lab experiment is to find the magnitude spectrum of a PPG signal using DFT, to compute the pulse rate of a PPG signal using DFT, to compute the pulse rate of the PPG signal using an autocorrelation function, and finding out the difference in error between them using the Arduino platform as well as MATLAB. So what is a discrete Fourier transform? So usually when you have a discrete sequence and you try to get the Fourier transform of that, you will get a continuous spectrum, right? And this continuous spectrum is periodic from minus pi to pi. Is periodic with a period of 2 pi, which starts from minus pi to pi and then repeats after that and before that. So if you really want to work with such frequencies in a computer, you need to discretize it, right? So you have to sample certain frequencies from the from the frequency spectra in order to store those particular frequencies and be able to work with them using a digital device such as a computer. So what a discrete Fourier transform does, it just discretizes the continuous frequency spectra which is obtained from the Fourier transform of a finite length discrete sequence. So the formula of the formula of DFT is x of k is equal to summation n is equal to 0 to n minus 1 x of n e power minus 2 pi j k n by n, and this k usually extends from 0 to n minus 1. However, it can extend more than this but not less than this. If you make this less than the number of data points you have, you'll get aliasing components, which will then make the signal very inaccurate. And the inverse discrete Fourier transform is calculated as follows. Now, one very interesting to note is x of k and x of n are periodic in nature. Now, initially it may be a bit counterintuitive, but if you go through the thought experiment, you can probably get to the solution. So you have x of n to be a finite length discrete signal, right? So if it's a finite length discrete signal, when you take the Fourier transform of that, you are going to get a continuous Fourier spectra which has a period of 2 pi, like we discussed before. So that is going to be from minus pi to 3 pi, 3 pi to 5 pi, etc. Now, what are we trying to do? In the frequencies domain, we are trying to discretize it. So if I wanted to discretize something, what would I do? I would just multiply it with an impulse train. So in the frequency spectra, all I do is I multiply it with an impulse train. However, when I transfer that to the time domain, it gets converged, right? I mean, multiplication, there's a very simple property, the multiplication in the frequency domain leads to convolution in the time domain. So since that property is true and we are discretizing the signal in the frequency domain, we'll be convolving the signal with the corresponding impulse train in the time domain. And since you're convolving, you are essentially repeating the signal after some particular time period tp. So let's say that you have a signal del t minus tp del t minus 2 tp and so on, summation of all of these, and you multiply it with say a single impulse. So now you'll get, so now I wouldn't say a single impulse, a single sinus, a single value, like suppose a 5 at 0. Now when you do this multiplication, you will get 5 at 0, 5 at tp, 5 at 2 tp, etc. So as you can see, it is going to repeat itself. Hence, if we do that to each individual component of the finite length discrete signal, you're going to get a repeated signal. Therefore, x of k and x of n are periodic in nature. However, for our calculation purposes, we ignore the points that are after n minus 1 and before 0 in both cases. And that is an assumption that can be done because we're not using any of the properties of that particular signal, such as convolution and such as convolution or multiplication as of yet. However, if you have to consider something like a convolution or a multiplication, then you have to go back to the fact that this is a periodic function and you can't do a normal linear convolution. You'll have to probably do a circular convolution with a discrete sequence, with this discrete sequence, in order to get the correct value. Now, to actually calculate x of k, as you can see, you can actually write this as a matrix. So the matrix is just this, and you can see that this follows a formula wkn by n, right? So what wkn by n is just this, power minus 2 pi I k n by n. And if you want to get the DFT, that is x of k, as a vector, you have an x of k, you'll multiply this particular matrix to the entire length of the signal, that is x of 0, x of 1, x of 2, blah blah blah, x of n, which will, and once this multiplication is done, that will give you this x of 0, x of 1, x of 2, x of n, x of n minus 1. So this is, and this really helps when you're using a computer, because it is much easier to do matrix multiplications. I wouldn't say easier, the computational capacity of computers to do matrix multiplication is sometimes much better than to actually do the computation using this particular method. So, and we have a lot of very nice software such as MATLAB or Octave that can do this matrix computation very fast. So it is more prudent to use a matrix method as compared to this. However, since we don't have those optimizations in this particular lab experiment, we will be going with the naive way to multiply the signal with this particular WKN by n. Now, I am not going to explain the autocorrelation function because that is something we explained in the last lab itself. So I'm just skipping this part. And yeah, let's come to the Arduino code for the DFT of the PPG signal. So what we essentially do is we take all the samples of the signal and pass them through a low pass filter, and that is again just done to reduce the high frequency components. And you have to get the DFT matrix, right? But to get the DFT matrix, you need to use something like an Euler's form of an imaginary number, that is e power 2 pi I j k n by n. The two issues with that is, currently in the Arduino platform that we have, we really can't use complex numbers without any clever tricks. So to actually do it, what is prudent is that you just split this into cos theta plus I sin theta. And although you still have to work with an imaginary number, that is I, you ignore it and get two different vectors that has a cos theta component and a sin theta component, and that is what is done here. So we get the real and imaginary part of the DFT by using the cos theta and the sin theta, and you get the magnitude spectra by just using the L2 norm of the cos theta as well as the cos theta component and sin theta component. That is basically root of cos square theta plus it's the magnitude multiplied by the cos square theta plus the magnitude multiplied by the sin square theta and the root of that. And after that, once you get the DFT, we try to get the maximum value. And the reason why we try to get the maximum value in that particular frequency spectra is the assumption that, I wouldn't say assumption, in any we have a in any particular signal there are a lot of frequencies, right? But we are trying to look at the most dominant frequency. So when we try to look at the most dominant frequency, you're going to plot every single frequency point and then try to find out which is the maximum value. So that is what we have done here. And we are saying that when you plot the magnitude spectra, the frequency that has the maximum value will be the dominant component in the signal. So now pulse rate was calculated as before we move on to that, you have to find out the highest index of that magnitude spectra in order to understand what the dominant component is. So once you have the dominant component, you can actually calculate the pulse rate, because then you get to know the time period. And like I said, in the previous case itself, pulse rate was calculated as 60 by the time period, and in our case it will be calculated by this. Now the funny thing is, you may be wondering how this comes up, right? So what happens is, when we get the index, we only get in terms of an index. And what I mean by that is, you have around n-1 samples, right? So you have something like 0, 1, 2, n minus 1. And if you get something like a value of 2, it makes no sense because it is not scaled to that frequency value. So all this is doing is it is scaling to the frequency value by multiplying this by fs. So the first index divided by the length of signal multiplied by the fs gives you the proper scaling thing. And this can be done by a reverse relation, that your discrete frequencies lie between minus half to half. So what we have done is, f by fs is equal to the index by the length of the signal, and this will always lie between So now this fs has got to this opposite side, and you get fs into first index by length of the signal. So that is basically what we've done. Now, and this is calculated. This is in beats per minute. Now the code is just as follows. Initially, we have just defined the data, defined a particular variable x, defined the total number, and we have defined the this W matrix. But since we can't work with Euler operations, it's only the real part as well as the imaginary part. And to actually calculate the DFT components, you have again split it into the real part and the imaginary part. And we also find out the magnitude response. And we have defined pi. So initially, we just pass it through moving average filter, and that code was done in the first lab, so I don't want to repeat it. And how do you compute the DFT? So your basic thing is you have to do a summation from this basic summation, right? Sorry, this one. N is equal to 0 to n minus 1 x of n e power minus 2 pi I k n by n. So you'd probably keep k constant for the first loop, and then sum over all your n's, and then change your k, and then sum over all your n's. That is what is being done here. It's a double loop. So for the k starts from 0 and k goes till n minus 1. You keep adding k after that, and then you first make this 0 in order to just reset those values. You don't have to do this, but this is just something like a safety that I use in most programs. Now you want to populate this matrix, right? So the matrix is populated as follows. The real part, so you can see that in this matrix you have w k n by n, and everything is just a multiple of that, right? The n's are increasing this direction, like w k n by n, and here they are decreasing. So that is what we have tried to emulate here. The we have again reset these values, and this k denotes the number of this k is for the number of rows, and this is for the number of columns. And all we have done is we have just multiplied. We have just got the matrix by just splitting it into the appropriate cos and sine components using the decomposition of the Euler e power I j theta. So again, imaginary part is the same thing. This is for the number of rows, this is for the number of columns, and we've got a minus because we have a e power minus j whatever k n 2 pi by n, sorry. And the real part, the real part of the x of k, the DFT, is got by multiplying that particular signal with the real part, and the imaginary part is got you get the imaginary part by multiplying the data points of the original signal with the imaginary part. But since you have summation, you end up adding this over all your n's, and to get the magnitude response, all you do is you take the L2 norm, which is what we've done here, and those are also added because it is again an L2 norm, right? You have to add for a vector. If you take the L2 norm, you have to add every single component. So now to get the peak value and the index of that peak, what you have to do is you just have to iterate over all your n's, and if peak is less than some particular magnitude response value, you find the peak and you get the index. So all you do is you first reset the values to 0, and then if your peak is less than the next value of the magnitude response, your guess of the peak was wrong, and hence you update your peak value, and then that particular value, which is n, becomes your index because that is assumed to be your index. And then you just calculate the pulse rate with the same formula that we have got before, and this is the plot that we have obtained from the DFT spectrum. Now the Arduino code for the autocorrelation of PPG signal is something that we have done before, which is more or less the same thing, and I'm not going to go through that because this was done in the last lab. And finally, the plot that we obtained through that is this, and this is the MATLAB code for actually computing the same thing that we have done before using an autocorrelation. The same thing that we have done before, that is computing the DFT as well as computing the autocorrelation. So first you pass it through moving average filter, which is the same thing that we have done before itself. So you just don't, all you have to do is sum over over the data components and divide by the filter window, which is done here. And if it's less than a particular size, if it's less than like the filter window size, then you only sum to that particular point. Else you sum over that particular point minus the filter window times. And that is done because there may be a time where, suppose your filter window is of size 4, and you have and yeah, suppose your filter window is of size 4 and you are at data point 2, so you can't really add a data value of 2 1 0 and then a -1, right? -1 doesn't exist, so you have to add only a 0 1 or a 2, depending on how you number your time instances. So this particular line is just so that you add zeros before it, so that there is no problem with the definition of your moving average. And to calculate the DFT and DFT matrix is very easy in MATLAB. All you have to do is just type FFT. I just type DFT matrix, and to get the max value like we have got before, all you have to do is write max ABS DFT, which is very easy. And once you get all this, you can easily plot this, and the plot is what you get here. Next, you calculate the same thing, that is what you've calculated before, that is the dominant frequency using the pulse rate, basically using the concept of the dominant frequency. And the autocorrelation function is again just got from first. Well, the issue with the autocorrelation function is first you have to make it a zero mean signal, and then you take the autocorrelation of that signal. However, in MATLAB, the XCOR function takes the autocorrelation of minus infinity to infinity. So you'll get a thing that's symmetric about this y-axis. That is the true autocorrelation. However, the issue is we don't want that in our case, because we want to find out this maximum value, right? So to do that, the length of the signal was 75, so you just take all the values from the 76 to the end and you get exactly half of the autocorrelation function. And to get the zero crossing points, that is these points, you just look at the next value, multiply it with the current value, and see if it's less than 0 or not. If it's less than 0, then you assume one of those points to be a zero crossing, and then you try to find out the maxima after that to get this particular value. So therefore, this particular time period that you get is your is basically the dominant time period of your signal, or you can say the dominant frequency if you look in the frequency domain. Now, this is the plot of the autocorrelation function. This is the plot of the DFT magnitude, and the pulse rate calculated by using both DFT as well as autocorrelation is 80 using DFT, and autocorrelation is 68.1818. Now, this is actually closer to the true value as compared to this value, and the reason for that is this signal was sampled at 25 Hertz, and 25 Hertz is a very low sampling rate to actually get any good resolution. So if your sampling rate is that low, then it is very difficult to compute your dominant frequency using a DFT. It is instead more prudent to calculate your time period that you have found using an autocorrelation function. And the reason for that can be thought as, in an autocorrelation function, irrespective of what you do, you're just multiplying two signals. You're not decomposing the signals into anything, right? You're just multiplying. And inherently, if you're just multiplying signals, if there is some repetition, if there is a particular repetition, then that repetition will get captured when you do the multiplication, irrespective of whether some data points are lost or not. And that is because by discretizing the signal into data points, you don't mess around with the periodicity of it. You're just maybe reducing the point size, and hence the inherent time, the inherent time period of that signal will not be lost. But in the case of DFT, since they are directly dependent on the Xn values, the values of your particular signal, if the discretization is not done properly, what is bound to happen is that, imagine that to get a perfect frequency, you need more points in this region. However, if you have, since you've done a discretization, you get 1 point here, 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 and you get 1 point here. So irrespective of what you do, you're going to get a maximum at this point itself, right? Hence, it's very data dependent, and therefore, if you have sampled it using a very bad sampling rate, it is more prudent to use an autocorrelation function to get the pulse rate or the period as compared to the using the concept of the dominant frequency in the DFT. So I think that is the end of the video. Thank you for your time.